Hi, welcome to the second video for Psych 5316. In this video, we're going to continue our work on Lab 1 with the flanker task, and specifically, we're going to learn how to plot the so-called conditional accuracy function. So let's get started. First of all, recall the context that we're in. In the last video and last class that we had, we developed a flanker task, which is based on the original paradigm developed by Erickson and Erickson in 1974. Remember that the basic idea is that when people are asked to respond to a stimulus that's surrounded or flanked by irrelevant stimuli, these irrelevant stimuli basically get in the way and they interfere with the response. So when you have a comparison of congruent trials and incongruent trials like these that we have talked about, the flanker effect is that your RTs, your response times, and your error rates increase on incongruent trials relative to the congruent trials. That's the flanker effect. In our experiment, which we described in the first video, we designed an experiment that was roughly based on Heitz and Engel 2007. Our stimuli were 5-letter strings consisting of S's and H's. That gave us 4 different stimuli, either all S or all H, both of which were congruent trials, or an H flanked by S's and vice versa, an S flanked by H's. Those were our incongruent trials. We put together 3 blocks of 80 trials each, giving us 240 trials total, and we imposed RT deadlines on blocks 2 and 3. And the goal here, we didn't really talk about it when we developed the experiment, but as you'll see today, the goal was to essentially spread out the distribution of response times, give us lots of fast trials and lots of slower trials, and even more importantly, give us the possibility of making more errors, because people tend to do really well on this task if you give them enough time to respond, if you give them enough time to think. But if you start putting RT deadlines in, you tend to make them mess up a bit. So our goal for today is to extend this work. We've done the experiment, we've collected the data, we've even talked about how to start analyzing the data in R. What we're going to do today is introduce a theoretical model of the flanker effect. Now remember, in the context of experimental psychology and cognitive modeling and whatever you want to call this, a theoretical model is essentially what we like to think of a theoretical model is a way to describe the mechanism that is responsible for the behavior that we're seeing. Okay, so we're going to talk about some possible reasons for why we see a flanker effect. And the one we're going to pick on today is the so-called attentional spotlight model. This is not the newest, latest, greatest model. In fact, there have been many refinements to this, but it's a good one for our purposes. And then we're going to describe an analytic tool that we can use to test this model. And it's called the conditional accuracy function, or CAF. And so finally, we're going to learn how to build the CAF in R. Now, the modeling that we're going to do is going to be graphical. We're going to look at a graph and use that to infer whether this attentional spotlight model is reasonable. We're not going to do any quantitative model fitting in this course. So let's talk about this potential model of the flanker effect. When you talk about behavioral modeling or cognitive modeling, what you want to know is you want to be able to answer this. Why do subjects perform worse on these incongruent trials? So far, we have seen that they do, right? We saw a huge flanker effect when we analyzed this data, but we now want to know why. Why is it that our subjects perform worse? So if we go back to Grattan et al. 1992, this is a very highly cited paper, and they explained it as follows. They explain it with what's called a spotlight of attention metaphor. So the idea is that if you think about the time that elapses from when the stimulus appears on the screen, early on, subjects may process both the target and the distractor letters together. Okay, so this is sort of a wide attentional spotlight, if you will. But then later, as time progresses, subjects are able to focus their attention onto that central target, which is what we tell them to pay attention to. So the idea is that this dynamic spotlight of attention is narrowing as time progresses. Here's kind of a classic picture. This comes from a paper of Jim Grange, and you see diagrams like this in papers as well. This spotlight of attention starts out as time starts. It starts out very wide, and the subject is paying attention to all of the stimuli. But then, as time progresses, that spotlight gets narrower and narrower, and then finally, in the later trials, the subject is able to pay attention only to the center stimulus. Now, what does this mean for the flanker effect? Well, if this attentional spotlight is true, this model is true, what does it mean for performance? Well, on fast trials, in other words, those that are relatively early in that perceptual process, these trials will be driven mostly by the distractors. And so subjects will make lots of errors on the incongruent trials. Why? Well, remember, on the incongruent trials, the distractors are not the same as the center target. And so if they're paying attention to those distractors, they're going to make lots of errors, at least relative to the congruent trials. But on slow trials, those where more time has elapsed, those trials, the performance will be driven mostly by the target. And so those error rates are going to decrease because by the time that attentional spotlight has focused onto the target, the distractors are no longer being paid attention to, and so the choice tends to be much more accurate. Now that sounds all great, but how do you demonstrate that this may be what's happening? Well, Grattan et al. Introduced something called a conditional accuracy function to demonstrate this model. So that's what we want to spend the rest of the time today talking about, is what is a conditional accuracy function, and more to the point, how do you construct it? So this is one of the original plots of a conditional accuracy function that was provided in the Grattan et al. Paper. And there's a lot more information here than what I really care about, but the basic idea is you kind of have two groups of graphs. Okay, you have these at the top, which are the solid dot graphs, and then you have these down here, which are the open dot graphs. In the context of our experiment, these at the top, these closed dot graphs, these are the congruent trials, whereas the open dot ones are the incongruent trials. Now this plot is constructed by putting response time on the x-axis and looking at how accuracy depends on response time. And what Grattan et al. Did is they divided the entire distribution of response time. So remember that basic, that skewed curve of response times that we've seen already. They divided that into 5 bins, okay? And then they looked at the accuracy in each one of these bins and plotted that on the y-axis. Now, why this is good is that this conditional accuracy function provides us with a very distinct behavioral signature of performance. Namely, accuracy on the congruent trials is relatively constant. Let's go back. Notice that the accuracy does increase from the faster to the slower trials. Remember, speed here is these are the fast trials, these are the slower trials. Accuracy does increase, but overall it's relatively constant, right? It's relatively a flat line compared to the incongruent trials. The accuracy on the incongruent trials increases a lot as RT increases. And so that's sort of see if I can get the hands the right way on the figure here. It's sort of a behavioral signature to have this constant increase in this constant accuracy for congruent trials, but this increase in accuracy for the incongruent trials. So if you see something that looks like this, this is support for that attentional spotlight model. The idea being here at the fast ones, you have a lot more errors or a lot less accuracy on the incongruent trials, but that difference between the accuracy decreases as the trials get slower. And the idea being, again, that as trials get slower, people are able to focus onto the target and make fewer errors. So how do we plot this? How do we get our own conditional accuracy function from our data? Well, there are basically 4 steps, and we're going to dive into R here in just a second and actually go through those steps, showing the code and everything. But the basic 4 steps are this. First, we have to split the RT distribution into some small number of bins, all right? And we'll be specific with what we mean by bins in a second. Once we get these bins, we are then going to compute a couple of things. We're going to compute the mean response time for each bin. And we're going to compute accuracy for the congruent trials and incongruent trials in each bin. So essentially, if you want to think about it this way, we're going to have 4 bins, and then we're going to have 3 numbers for each bin. We're going to have a mean RT, we're going to have an accuracy for congruent trials, and an accuracy for incongruent trials. Then we'll go to bin 2, and we'll do exactly the same thing. And once we have that, we actually have all the data we need for the CAF. We can then plot accuracy as a function of mean RT, and we'll do separate lines for each condition. And so once you kind of get these 4 steps embodied, then you're ready to jump in and do some coding. But before we jump into R, okay, I want to be very specific about this first step. How is it that we split this RT distribution into bins? Well, what we're going to do is we're going to split our distribution. You can actually see this distribution down here. We're going to split that distribution into 4 bins. And the way we're going to do that is we're going to find what are called the quantiles of the distribution. Now, you can look this up in any stat book. But a quantile, so let's be specific. If I said I wanted the 25% quantile, what that means is that is the point of the distribution that is greater than 25% of the distribution. Okay, let me do this again. Let's suppose I want the 50% quantile. That's the point on the distribution that is greater than 50% of the data. And then similarly, the 75% quantile, that's the point on the distribution that's greater than 75% of the data. Now, that looks like not enough, right? If I want 4 bins, why do I only need 3 quantiles? Well, you can see why in the picture down here. What I've done is I've taken a sample of the data that you're going to look at. This will be very similar to what your picture looks like, but not exactly the same. And I have computed these 3 quantiles. These 3 quantiles are represented by the red dotted lines that you see vertically. So you can see the first quantile is slightly less than 400 milliseconds. The second quantile, the 50% quantile, is right around 460 milliseconds. And then finally, the third quantile, or the 75% quantile, is right here around 520, 530 milliseconds. Now, those 3 points split this distribution up into 1, 2, 3, 4 sections. Okay, it's just like the old fence problem from algebra. If you want 4 sections in the fence, you need how many posts, right? It's not always equal to the number of sections. In this case, if I want 4 sections in the distribution, I need 1, 2, 3 dividing points. These dividing points are the quantiles. And since I've done it this way, this now tells me that this part of the distribution is exactly 25% of the response times. This part is 25% of the response times. This part is 25%, and finally, this part is 25%. So we're going to use that quantile function in R to split our distribution into these 4 equal sections, or these 4 bins. And then remember our other steps. We're going to compute the mean RT for these trials, the mean RT for these trials, and then these trials, as well as accuracy for these trials, these, and these. Okay? So at this point, we're ready to jump into R. So let me flip into R real quick. What you need just to start with, what you need is you need to start with what we did in class last time. You need a data set that we called clean. Remember, this is all of the raw RTs. We filtered out the practice trials, and then we also did a mutate command. Remember, we called the variable response underscore time. We just called it RT. So again, you need the clean data from the lecture in class last time. Okay. So once you start with that, okay, we're ready to work on these conditional accuracy functions. The first thing that we're going to do, so I'm going to do all of my work over here in the script editor, and then I'll pass things into the console. And remember, we'll see our environment down here as we develop variables, and finally we'll see some plots once we start working on the CAF functions. So the first thing we're going to do, if you've got that clean variable built, we're going to attach it to the workspace. We're going to do that so that we can easily call variables from that data set. So we just do that using the attach function. We'll say attach clean, and then we'll remember control enter or command enter if you're on a Mac. Control enter will make that happen. Okay. Now, this is nice. In fact, we can check that this works. If we just type in RT over here in the console, it should recognize that, and it should give us a whole bunch of response times. In fact, more than it wants to show us. Okay. Okay, so first step was to divide the RT distribution into 4 bins. All right, and the way we're going to do this is the quantile function, and I'm going to name the bins. I'm going to save them in a variable. So here's what I'm going to do. I'm going to type in bins equal, and I'm just putting spaces in to make it easy to read. Remember, the spaces are optional. I'm going to say bins are equal to quantile. That's the function. And the quantile function takes in the data set, which is RT. And then it needs to know which quantiles do you want, and that's the probs argument. So I'm going to say probs equal, and I'm going to give it a vector of 3 probabilities, 0.25, 0.5, and 0.75. So this is the 25%, 50%, and 75% quantiles. And once I do control enter, you'll notice now I've got a variable named bins, and these are the quantiles. It says the first quantile was at 391 milliseconds, the second one is at 464, the third one is at 531. So that seems to work. Okay, so that's the first step. We've now divided the distribution all in one command. But what are we going to do with it? Well, remember, what we're going to do with it is the second and third step. We're going to compute a mean response time for the first, second, third, and fourth bins. And we're also going to compute accuracy for both congruent trials as well as incongruent trials for each of those 4 bins. Now, we can do that, but more importantly, one of the things that you need to think about when doing programming like this is you need to have a data structure to store all of this information in. So if you remember when I was describing what all we're going to do, I was using my hands to do something very specific. What I was saying is we're going to have 4 bins. So I'm going to visualize those as 4 columns, all right, if you will. And each of those bins is going to have 3 numbers, a mean response time, a accuracy for congruent trials, and an accuracy for incongruent trials. So essentially this is like a 3 by 4 matrix, and that's exactly what I'm going to build. I'm going to build a matrix. I'm going to call it CAF data. All right, notice how I capitalized the D. That just makes it easy for me to read. No spaces, you don't want any of that stuff. So CAF data, I'm just going to make that an empty matrix, and I can do that by saying matrix, okay? And then I need to tell it the number of rows and number of columns. So in row is the number of rows, and in col, N-C-O-L, is the number of columns. And so if I execute that command, control enter, I now have a matrix. And in fact, if I go up here to my console and just type in CAF data, you'll notice that it gives me a structure similar to what I'm imagining. I've got 4 columns and then 3 rows for each of those columns. So my columns are my bins, and then my rows are my mean response time, accuracy for congruent, accuracy for incongruent. Now they all say NA, right? They have nothing in them at this point, but I've built this blank data structure that I can now start putting things into, and once I fill it up with the right data, then I can go and I can call a plot from that little data set, from that little data structure. So that's a very important first step, is to start with an empty data structure. Okay, let's clear out this console just a little bit. If you remember how to do that, that's Control L, and clears out the console. So what I'm going to do is I'm going to do my first bin first, right? So this is the bin where all the response times are less than 391. Okay, so I'm going to just make myself a little comment in the script. I'll say first bin. Now the thing that I need to do is I need to tell R what data I want to consider as the first bin. Now remember, my definition of bin is anything that is in that first quantile. That is anything where the response time is less than 391 milliseconds. Okay, so the way I'm going to do this is I'm going to make myself a little subset. I'm going to call it temp. Anytime I've just got a little temporary sort of throwaway file, what I like to do is just call it temp. All right, so I'm going to say temp, and it's going to be a subset of my data file clean, and the subset is defined as RT is less than the first bin. All right, so bins 1. What is bins 1? Well, bins 1 is just a fancy way of saying the 391 milliseconds. But instead of typing in 391, if I was to do this on another data set, it would no longer be 391. So I'm going to use the variable here, bins 1. All right. So if I execute this, all right, then I get my little temporary file. You notice it is smaller. It is it accounts to 1,117 observations. Okay. So that is about a quarter of my data set. Now what are we going to do with this? Well, what we're going to do is we're going to find the mean RT, and we're going to find the accuracy, and we're going to assign them to positions in that blank matrix. So remember, the structure of my matrix is a 3 by 4 matrix. Okay. So the first thing I'm going to do is I'm going to say right here, I want this first row. I want this first row to be my mean RT. Okay. So I'm going to say calf data, but I've got to tell it which one. So the way you get this specific spot is you say what the row index is and the column index. Well, as you can see here, this is the first row, first column. So calf data 1, comma 1 will simply be, I'm going to say equals, mean of the temp file RTs. Okay, so I specify temp $RT to tell it to take the RTs from that temp data file and then just compute the mean of them. So if I execute line 8 as I've typed it, okay, now notice now that calf data has a number in right here. This is the mean RT for that first bin. And I'll do that for the second bin, third bin, fourth bin, etc. But what I'm going to do here is I'm going to go ahead and now compute my accuracies. Okay, so the accuracy for is going to be in 2 rows, right? I'm going to make the second row my congruent trials, and I'm going to make the third row my incongruent trials. So I'm going to say calf data 2, 1. Right? So this is row 2, column 1. That's going to be equal to my accuracy. Unfortunately, there's no quick function for accuracy like there is mean, right? The idea with accuracy is you want to add up all the correct trials and then divide that by the number of trials, period. Now, the quick way to think about this is not the right command, but I want to show you kind of how it works, is I just say the sum of temp $correct. Remember, correct is a let's just look at it real quick. Temp $correct should be a bunch of zeros and ones, right? So 1 means correct, 0 means incorrect. So a quick way to get the total number of correct trials is just to say the sum of, we'll do this in the console, sum of temp $correct. That tells me that there were 659 correct trials. Now, how many is that out of? Well, that's out of, we can see down here, 1,117 trials, which I can get by simply saying the length of temp $correct. And so now that tells us that to compute accuracy, all I need to do is take the sum of that correct variable, temp $correct, and divide by the length of temp $correct. Okay. Now that's great, right? And that'll give me a nice fraction. In fact, you can try that here. I'm going to do it in the console because it's not quite correct, as I'll show you. But if I type in that command, sum divided by length, that gives me 0.589, so 59%. But unfortunately, that doesn't quite get what we want. We want different we want different accuracies for congruent trials and incongruent trials. So we need to be a little more specific. We need to tell R that we only want the correct trials that correspond to congruent ones, right? In other words, we want the condition to be congruent. And same thing with this length command. So the way we do it is quite simple if you think about it that way. We're going to say, take the sum of this variable, but only those corresponding to where condition is congruent. All right? That makes sense conceptually. In terms of typing the command, it gets kind of ugly, so bear with me. What I'm going to do is I'm going to basically have a quick way of subsetting this correct variable. So see my cursor is right there at the end of correct. I'm going to put in a square bracket, and I'm going to say temp $condition double equals quotes congruent. Okay. Now what that's telling R is find the temp correct variable, but subset it only on those where condition is equal to congruent. Now why the double equals? Remember, this is a logical test. I'm finding those that correspond to a particular value of condition, namely congruent. So I have to put in double equals. If you put in a single equal, it won't work. So put in the double equals. Now, I've done that here. I also need to do it on my length command. So I'm just going to copy the part that includes the brace, and then I'm going to go here to the end of the line. And again, right there after correct, I'll paste that in. Okay. So it's a really long command, and you might have to play with this a couple of times to get it right. Okay. But basically, it's sum divided by length, and you're just having to be really specific about the thing you're taking the sum of. Okay, that's this thing, and the thing you're taking the length of. They will match. Okay, whatever you have that's highlighted here for me right now, that'll be the same as over here. Okay. So once you think you got it right, go ahead and do Control Enter. Didn't give me an error. In fact, if you look at CAF data, remember my matrix, I now have a fairly convincing looking error rate, right? This list looks good. So it's telling me that in the first bin, my accuracy, remember this is accuracy, this is number correct, not the number of errors, my accuracy was 67%, which is not very good, but again, this is fast trials, right? So people make a lot of errors on these. Now, the last row is going to be the accuracy on my incongruent trials. Remember, we specified congruent here. Well, the nice thing is accuracy is still accuracy, right? It's going to be done exactly the same way. So I'm just going to click that entire line, and I'm going to copy it and paste it. Okay. Now I just want to change a few things. All right. I want this to be the third row, not the second row. And then I want the condition to be incongruent. So I'm going to go and change all the congruence in this row to incongruent. Leave everything else the same. You know, if it works up here, it'll work down here. Just change the row to 3 and change the condition to incongruent. And I'll do Control Enter. And then once again, I want to look at CAF data, and you can see I've got now for my first bin, I've got the mean RT, I've got the accuracy for congruent trials, and I've got the accuracy for incongruent trials. Okay, are you sweating yet? That's just the first bin. But with a lot of things in programming, and this is no different for R, once you've done it once, it's easy to modify it for subsequent bins. So here's what I'm going to do, guys. I'm going to copy this entire code chunk, and I'm going to skip down here, and I'm going to paste it, and I'm going to just edit it. So this is my second bin. I'm going to do it in exactly the same sort of programming flow. I'm going to define a temporary data structure, and then I'm going to assign the mean and then the accuracies to parts of my CAF data matrix. Okay. So let's work on line 13 first. Line 13 is my temporary data file. So I want to take the subset of clean, but this time I want the RTs to be between the first and second quantiles. Okay. In other words, the RT needs to be bigger than the first bin's value. Remember what bins was. Let's type it over here. Bins was my 3 quantiles. I want it to be bigger than 391, but less than 463.5. So I'll say this. I'll say RT is bigger than bins 1, and, so and in R is the ampersand, and RT is less than bins 2. Okay, so remember, that tells me that I want RTs bigger than 391, but less than 463. On the picture, let's just look at the picture real quick. That's this second bin right here. Okay, what we did before was on the first bin. Now I'm on the second bin. Okay, so that'll work. Let's should work anyway. Let's do Control Enter. Okay, and didn't throw an error. That's good. Now CAF data. All of these computations are going to be the same because they're based on this temporary data file that I've just built. The only thing that's different is the position in the matrix. So let's look at our matrix again. What I want now is I want 3 numbers, but instead of putting them in the first row, I want to put them in the in the first column. I want to put them in the second column. So to do that, I just need to change this second index to 2 on all 3 rows. Okay. It's still first row, second row, third row, but now I'm going to have column 2 for all 3 of them. I'm not going to change any of the other stuff, and I'll just hit Control Enter for each of those 3 lines, lines 14 through 16. And if I look at CAF data again, you'll notice I now have a mean RT, and I have accuracy and accuracy. All right, third bin. We'll copy the second bin, we'll paste it down here. I'm going to call it third bin. Now this time, what do we change? Well, we need to change what the temporary data file is. We're going to take a subset of clean, but this time we want the RTs to be bigger than bins 2, but less than bins 3. Remember, if we look at bins, we now want them in between this 50th and 75th percentile. We want it bigger than 463.5, that's bins 2, but less than 531, that's bins 3. So that's line 19. We'll execute line 19, and then like before, we want, let's look at CAF data one more time. We want to now fill up this third column. So we'll change the index, or the column index, to 3 on each of these 3 lines, 20 through 22, and we'll execute them. And then we type in CAF data, And you can see that once again we have filled out our column with the appropriate information, a mean response time and then accuracies. Okay, let me go here. I have to go to the end to, for some reason, there's a little bug with my version of RStudio. All right, so last time we're going to now copy, I'm going to call this the fourth bin. This time in the fourth bin, I want all the RTs that are just bigger than that third bin number, all right, that third quantile. And so that's all I've got to do on this one is I say that the subset is RT is bigger than bins 3. Remember, bins 3 is 531, so all the RTs bigger than 531 will get into this structure. And for CAF data, I'm going to put all of these in the fourth column. So I'll change the column index on those 3 lines. So we'll execute, 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 execute. And now, if everything has gone right, if I type in CAF data, and let me scoot this over just a little bit, you can now see that that data structure is exactly what I want. I have 4 columns corresponding to my 4 bins. I have the first row is the mean response time, second row is the accuracy for congruent trials, and the third row is the accuracy for incongruent trials. The only thing left to do now is step 4 in our plan earlier, and that is to plot these things. So how do we go about that? Well, we're going to use the plot command. We're going to get kind of fancy with the plot command, though, so this will be fun. You're going to learn some advanced techniques here. So if you were to just plot this stuff, it would be kind of ugly. I'm going to actually do some things that make this graph really kind of nice, and nice that we could export and put into a publication if we so desired. Okay. So this last part I'm going to comment as construct CAF plot. And I'm going to give myself a little bit of room down here. Okay. First thing that I'm going to do is I'm going to define some stuff that will make the plot look good. Basically, what I want to do is I'm going to define my range of my plot to be based on what these mean RTs are. I want it to be a little less than 289 for the lowest end of my plot and a little bigger than 622 for the biggest end. So what I'm going to do is I'm going to define a couple of quick little variables here. I'm going to say min RT, and I'm going to say that that's going to be 90% or 0.9 times the minimum of this row right here. Right? This row is CAF data 1, comma. All right, notice if I just say 1 comma, that gives me the entire row. So I'm just going to say take 90% of that minimum. And you can see down here that's around 260. So it's going to be just a little bit to the left of our smallest RT, which is 289. And similarly, I'm going to say max RT is going to be 10% more than the max. Or in other words, 1.1 times the max of that row, CAF data 1 comma. And so that max RT is going to be 684. Again, a little bit to the right of our actual max RT. So that's just going to be some parameters that I'll use in building my plot here in just a second. So we're going to use the plot function. How does the plot function work? Well, remember, if you want to see how something works, go into the console and type $plot. And it's very easy. In fact, this is like the most basic plotting command in R. It's just generic XY plotting. Basically, you've got to tell it what the X variables are and what the Y variables are. Okay, so let's think about this before we start typing commands. I'm going to go back to the presentation file, and let's look at Grattan et al.'s conditional accuracy function. The X values are the RT bins, okay? The Y values are the accuracies, okay? So where do we have those stored? Well, again, if you look at our data structure CAF data, you'll notice that the response bins are in the first row, okay, the first row of CAF data. And then the accuracies are in the second and third rows, respectively. So what we're going to do is we're going to do a plot. We'll type plot. The X's will be the RTs, which, as we said, those are found by taking CAF data and restricting to the first row. So again, it looks like it's incomplete because we haven't specified the column index. But remember, that gives you the entire row. So those are all the X values. And then we'll put a comma after this. And then we'll say that the Y values, well, those are going to be the CAF data, but they're going to be the second row. These are going to be the congruent trials. Now if I just plot this, let's just see what it looks like. Okay, I'll just hit Control Enter. And I'm going to move this up here and give myself a little bit bigger plot. All right. This is kind of an ugly looking graph, and this is not the whole story at all. So we're going to make this look a little bit better. I don't like these labels. I don't like the x-axis. I don't like the y-axis. I don't like any of it. Okay, but it does give us a start. So the way I'm going to do this is I'm going to start adding options to this plot, and these are just options that'll make things look good. Okay, I'll explain them as we go. So every time I add a new option, I start with a comma, and then I'm going to go down a line each time. So the first option I'm going to do is define my x and y labels. So I'm going to say xlab equals, and then in quotes, I'm just going to put what I want it to say. And RT with parenthesis ms. That'll be RT in milliseconds. That looks pretty good. Okay. So if I do Control Enter, that gives me a better x-axis label. Now I'm going to do the same thing. I'm going to do ylab, and ylab this time is going to be accuracy. Now there's some other things that I'm going to do. If you look at Grattan et al.'s plot, it had lines between the dots, so I want to make that happen here. To do that, I'm going to say type equals quotes B. Type equals B tells R to do both points and lines. Okay? In fact, let's see what that looks like. So that puts in your lines very nicely. And in fact, I like the way this does it better than some other options because it puts a little bit of space in between the dot and the line itself. I think it's just visually appealing. Okay. Now, I don't like the open dots for my congruent trials. I would like a closed dot. And so the way I change that is with an argument called PCH. And the PCH, what you do is you input a number. And if you Google R PCH, you'll get a whole list of possible markers for these points. And it just so happens that the one I want is number 19. Okay? So I'm going to say PCH equals 19. I'm going to say LTY equals 1. LTY is line type. 1 is a solid line, okay, and that's what I want by default, but I like to be very specific when I'm coding like this, just so that I know, hey, I was specific that I wanted a solid line. And then finally, I want to define those limits, right? So xlim, that's going to be the limit on my x-axis. That's going to be a vector from min RT to max RT. Remember, these are the ones that I defined up here in lines 31 and 32. And then I can do something similar for the ylim. I'm going to set ylim as, well, it's accuracy, so I'm going to set it from 0 to 1. And I think that's enough. So I'm going to go back up here, just somewhere in my plot command. I'm going to hit Control Enter, and that, I think, is a much better looking plot. Okay. So there is my accuracy function. There. Let me do this one more time. There we go. So you notice when I made the plot a little bit bigger, the label 1 actually showed up. It wasn't here before. Okay, so that looks pretty good. This is the CAF, the conditional accuracy function for congruent trials. And we'll put a legend in here in just in a few minutes, but that's what we want. Now we need to add some lines for the incongruent trial. So I'm going to say a comment. I'm going to say add incongruent data. And again, the only purpose of comments is so that I know later when I look at this script, hey, that's what I was trying to do here. The way I'm going to do this is not with another plot command, because if I did that without a little bit of extra work, it would actually erase this plot. I just want to add some new lines to it. So I'm going to do that with the lines command. All right, let me get this little thing out of the way. Okay. And we're going to say lines. Now, the syntax of this is very similar to plot. I need to define the x variable. The x variable is, again, calf data 1. That's the first row of the calf data. Those are the RTs. But then the y will be calf data 3, comma. Because remember, the third row of my calf data structure is my incongruent accuracies. Now, just like before, I'm going to use type equals B so that I get both dots and lines. This time, I want my dot to be an open dot, and that's PCH1. And I'm also going to use a different line. I'm going to use a dashed line, and so I can use LTY2. And that's really all I need to do here. If I do that little chunk, hit Control Enter, then that will give me my incongruent trials. Now you can see already that this is starting to look like support for the shrinking spotlight, or the spotlight of attention model. Notice that for the fast trials, there's quite a difference in errors between the congruent and incongruent trials, but that tends to decrease as you go on into your slower trials. The idea being that the spotlight of attention has now narrowed in as time progresses. So this looks like support for that initial model of the flanker effect. But we're not done, because how does the reader know that this is congruent and this is incongruent? We need a legend. So oddly enough, I'm going to say add legend. The command for doing a legend is called legend. And the way this works is you tell it where you want to put the legend, what you want it to say, what are the dots, what are the lines, etc. Okay. So here's what we're going to do. I'm going to say let's put the legend about right here. So that's going to be around an x-coordinate of 500 and a y-coordinate. I'm going to put the corner about right here. So that's about 0.3. You can put this anywhere. Play with it and see what you like. But I'm going to say x equals 500, y equals 0.3. Now, what do I want the legend to say? Well, I want it to say two things. And so, again, to do two things, I need to use the C function to make a little vector. And the first one is going to be called congruent. And the second one is going to be called incongruent. Whatever you type here is going to show up as the legend. So I'm going to say congruent and incongruent. Now, which one's which? Well, we need to tell it there are two things that are varying here. The PCH is different, and the LTY is different. So what are the PCHs? The PCHs are going to be 19 and 1 in that order. All right. Remember, 19, that was the solid dot, and that's going to correspond to my first legend entry, congruent. And then 1 was this open dot. That should correspond to incongruent. Same thing with LTY. LTY will be 1 and 2. Okay, just like that. And then this looks pretty good. That should do it. That's sort of the minimal amount of information. If we hit Control Enter, okay, you get that. I don't like that border. Okay, so you can actually remove the border. If we just say BTY equals N in quotes. Okay. Now, unfortunately, because the way R builds graphics is on top of what you've already done, it doesn't erase the border. But if you were to go up here and start with line 34 and then highlight that entire chunk and then Control Enter, it would build it from scratch, and you'll notice the BTY equals N now takes that border away. So all of that you can see right there is the code that's needed to make what I think is a pretty darn nice graph. Okay. So the last thing to do for you pragmatically as you start thinking about wrapping this project up and beginning to write a manuscript about it is how do you get this out of R and into something that you could put into Microsoft Word or LaTeX or whatever it is that you use to write your papers. Well, in RStudio, there's a really nice way to do it, and there's a little export button here in your plots menu. So here's what I recommend. What I recommend is that you save it as an image. Okay. And then now you'll need to tell it what directory to save it as. So I'm not going to be specific here, but it defaults to whatever your root directory is. So be sure and pick a directory that you have access to, like your desktop or a project directory or something like that. It gives it a default file name. You'll probably want to change that. I'm going to call this CAF. Okay. Don't put the extension on it because the extension will be automatic. By the way, you can choose any of these 5 options as an extension. I like PNG. You can also use JPEG. That's okay. I wouldn't use any of the other ones unless you know what you're doing. And then finally, you can change the aspect ratio of these things. I always like to start with a 600 by 400 for a graph like this. All right. Now, I said update preview, and it made it go away. So that's because my resolution of my screen wasn't quite big enough. But one thing that you can check is view plot after saving, and it'll open it up. And now we can see there's what that graph looks like. And it's pretty nice. Okay, so I'm gonna keep that. But the nice thing is that's now a file that it's saved on my computer, and I can import that into Microsoft Word or into LaTeX or whatever it is that I use for my manuscript writing. So that's that. We have done our 4 steps. We did the splitting of the RT distribution into bins. We computed mean RT and accuracy for each trial type in those bends, and then we plotted accuracy as a function of mean RT, and it looked something like, we'll go back to our studio, it looked something like that. So that's what you need to do. Hopefully that helps, and if you have any questions, of course, always let me know, and we can go back and take a look at it. If something's not working for you on the code, pause the video and look. The resolution should be good enough that you can see each line. Make sure your commas are in the right spot. R is powerful, but it's also cranky and doesn't tend to like you typing things wrong. So just be slow, be methodical, and you'll learn how to do some really cool stuff here. So that's all for now, and we'll see you at the next video.